So today we are going to have something on special semiconductor devices, and having discussed from the previous sessions on something on feedback, so we are going to dig deep into some of the components that are used in those circuits. So having the topic on semiconductor devices, and these are the only things that are useful also to make the feedback. So the first component we're going to do is what I refer to as Varactor Diode. Varactor Diode. So from this is that the first thing we need to be aware of when we see the diagrams, which kind of component are we supposed to be detecting or interpreting the diagram to be. So we are going to have this Varactor diode as one of the special semiconductor devices. They are special in the case that they are only used for specific purposes, other than the normal way they operate. So they are operate in a different manner and perform the same purpose as a different device. So their special is a certain way. So we're going to have the first thing we're supposed to do is to know the symbol of a Varactor diode. So that's how the Varactor diode looks like. And also the equivalent circuit for this Varactor diode. So the equivalent circuit will appear like this. So this is the equivalent circuit. So when you look at this, we're going to realize that the equivalent circuit has a variable capacitor, and then this one is the symbol. So how can we be able to use this Varactor diode? So it's just a similar diode that's normally reverse biased, but it's able to give us capacitive effect. So we talk of the variable capacitor. So from the term Varactor, from the term Varactor, we obtain what I refer to as VAR, which I refer to as a variable, and what I refer to as COR comes from the term referred to as capacitor. So generally, the diode is reverse biased. So this is a normally reverse biased diode. Reverse biased PN junction diode that is able to offer the capacitive effects across its junction. So we're going to have the sketch of the diode so that we see how it's reverse biased and also the characteristics. So let us have a sketch of the diode first. So this is a voltage supply, and the negative terminal of the supply is connected to the P semiconductor, and also the negative is connected to the positive terminal of the supply. the end semiconductor is going to positive negative terminal of the supply. At this junction here, we will refer to as the PN junction. And when this is reversed, the electrons tend to be attracted away from the junction, and that's why we form whatever referred to as a depletion layer or the barrier. Depletion layer or the barrier. So when we're having a characteristic of this, then we're going to have a sketch of how then this we expect it to behave. This is junction capacitance, and this is a reverse bias voltage. Reverse bias voltage. So the operation is such that when the voltage is connected or reversed across the PN junction, the electrons are attracted away from the PN junction, and therefore they form a depletion layer. Now that when we have reformed the depletion layer, we want to vary that depletion layer depending on the negative supply voltage. So when this voltage is increased towards the positive, the depletion layer changes. The depletion layer changes such that the depletion distance between these, so that the distance here is going to be changed depending on the voltage that we're going to apply. So when you apply a voltage from the negative towards the positive, the depletion layer is reduced. When the depletion layer is reduced, then the distance between the barriers, between the distance of variation of the barriers is now changed. And when that changes, we are going to have a change in capacitance. We use that principle to determine whatever as a variable capacitor. And that's why from the symbol, there's a variable capacitor that's connected in series with the resistor. So we're going to have our second special semiconductor device, which part as unit junction. Unit junction transistor. Equally, we are going to start by drawing its symbol. This is the symbol you are going to see when you're going through references. But we can have whatever as the similar diagram, but with the constructional approach, so that we have the construction that appears this way. This is the whole chip. We shall have this. And this is that. These two. This one. And this we shall have this as E. So this is maybe this an NPM, this is an N material, can be different materials, so that we have a unit junction. So the meaning of the unit junction is that this is a transistor with only one junction. You know that transistor is supposed to have two junctions, but in the normal case, but in this case, this is a type of transistor that's only one junction. So when the junction is operated, then it's able to conduct. So it's such that it's a three-terminal device. When described about the construction, it is a three-terminal device. It is a three-terminal device that has only one junction. Three-terminal device. The three-terminal device are the base 1, base 2, and the 3 is a three-terminal that has only one PN junction. One PN junction. So what about this? This is meant for the construction. So we can have something here that. What about the construction? It consists of an N material sandwiched in a P material at the middle to produce a single PN junction. The emitter is connected the emitter is connected at the middle, i.e. maybe at the N material. So from here we are going to have what I refer to as the equivalent circuit for this, so that we can be able to see that. So when you look at this diagram, we are able to see that for us to have a pure unit junction, we only need to get a pure substrate and sandwich with another pure material in the middle. So that one we shall only have an PN junction. Where we have got the sandwiching or the pasting of the different material, the middle is where we connect the emitter. This now forms what I refer to as the emitter of the component. And when it comes to operation, then we need to have a picture of how the circuit operates. So we're going to have the equivalent circuit, then we are able to explain from that. So UJT equivalent circuit. This is RBB. So when you look at this diagram, we have the RB1. RB1 is the base resistance, and RB2 is also the resistance. So the RB1 and RB2 are connected across a VCC. And because the resistance between RB1 and RB2 act as a potentiometer, then we talk of the RBB. RBB is the resistance between the base terminal 1 and the base terminal 2. So it becomes RBB. And also on this other end, there's sometimes written here as VD. VD is the voltage drop across the diode, which forms the PN junction there. And the VE is the voltage applied on this. So the diode resistance represents the PN junction. The diode resistance represents the PN The diode represents the PN junction, while the resistance Y, while the resistance RB1 and RB2, but the resistance RB1 and RB2 is the resistance that forms interbase resistance across the terminals. So therefore when RBB is, from the electrical analysis, is RB1 plus RB2. So RBB is the interbase resistance. So when there is no voltage applied, the UJT value resistance RBB, it is supposed to be the total resistance when there's no voltage applied. Then we need to understand that when no voltage is applied, the resistance across RB1 and RB2 is supposed to be given as the resistance across RBB. The resistance across RBB. And it varies with the applied voltage VE. And it varies with the applied voltage VE. So for us to help this, to make this, for us to make the UJT conduct, then we need to connect some voltage and have some condition for it to operate. So we are going to have something referred to as the operation of this, so that we are aware of what kind of, how the device operates for us to use this effectively. So we're going to have another diagram to explain the operation. So this the circuit that you can use to have the operation. So for us to bias the PN junction, they need to have whatever as the bias voltage. And when you look at this, the output terminal is connected across VBB, very referred to as interbase supply voltage VBB. And we still have the other circuits as previously described. And in this case, we'll also going to have another voltage across the emitter terminal, which is across the PN junction, connected at the center of the RB1 and RB2. When you look at this, then it's very easy. So for us to be able to get the diode voltage, the emitter diode voltage, remember the emitter is reverse biased. And we need to overcome that reverse bias voltage. So the emitter diode is reverse biased. The emitter diode is reverse. The emitter diode is reverse biased by the voltage drop across it. By the voltage drop across it. And this voltage drop across it is a function of the VBB. This voltage drop is given by the voltage drop across RB1, which you are referring to as new VBB, where nu is the intrinsic standoff ratio, intrinsic standoff ratio given by this one is supposed to be RB1 over RB1 plus RB2. So this reverse bus voltage, because this reverse bus voltage adds on the voltage drop across the diode. Therefore, the minimum required voltage, the voltage required for reverse bias is given by, we shall have this VBB plus the voltage across the diode. So this is the total voltage that will reverse bias this circuit, because it's going to be additive to the voltage drop across the diode, which is also reverse bias. So for us to turn this into operation, then the applied voltage that we're going to have must overcome this. Because remember, from the circuit here, the voltage drop across here and the voltage drop across here is the one that reverse biases this device. So we must apply a voltage that is greater than the 2 here for us to turn it on. So if the applied voltage is greater than the intrinsic standoff ratio of VBB plus the VD1, then the intrinsic standoff ratio of VBB plus VD1, then the device is turned on. Then the device is turned on. So as long as the voltage is below the UJT will remain off. So the voltage at which the UJT turns on is normally referred to as the pinch-off voltage. The voltage at which the UJT turns on is normally referred to as pinch-off voltage, or peak, not pinch-off, peak voltage. It's normally referred to as the peak voltage. VP. So the minimum voltage VP is supposed to be given as this VBB plus VD. So that's the minimum voltage required as the peak voltage. So we are going to talk about the UJT characteristics. VI means voltage current characteristics of the UJT. So we elaborate this using a diagram.
Elaborate this in a diagram.
Then we shall be able to have the diagram. So we're talking about the emitter voltage.
And we're talking about
The emitter current here.
so
This will have several sections
so that we were
able to, let me extend my drawing so that we have this. So we're talking about
the statement here.
this area here is referred to as the cutoff. And this area is the negative resistance region. Resistance region. And because there's a peak here, this is the peak, maximum peak it can go. We talk of the peak current. And this is the minimum current we are going to have here. So this is happens at saturation when we talk of the valley current. And here there is talk of the voltage at which this one appears is the peak voltage. And this one is the valley voltage. So this point is a valley. So for us to have greater understanding is that at this point here, the voltage at which the voltage that we are applying is below the peak point voltage, and because of that, the transistor is at cutoff. The meaning of cutoff is the transistor is still not conductive. We must overcome that voltage. So until we achieve that voltage at this point here, then the UJT is off. When you slightly exceed that voltage, then the UJT turns on. When it turns on, there's a drastic drop in the PN junction resistance, and therefore there's a negative resistance region here. That means if the resistance is going to go low, then the current is going to increase. The current is going to increase from the IP to IV. Because this current here is increasing, given that the resistance is going down because of the intermodulation. Then we are able to have what I refer to as this is a characteristic. So we need to explain the various sections, the cutoff, the negative resistance region, and the saturation region. This region here, we talk of the saturation region, whereby irrespective of us increasing the voltage, the current is already at maximum. The current, instead of increasing the current, already the voltage is maximum. So we only play around with the junction. So we are going to explain that in details. So we are going to talk about the cutoff region. The cutoff region. The cutoff region. So at this region, what do we to understand that the emitter voltage is below the peak point voltage? At this region, the emitter voltage is below the peak point voltage, and the UJT is off. And the UJT is off. So we're talking from the cutoff region, we have the negative resistance region, negative resistance region,
it's where there's a downward trend on the curve. The emitter voltage
decreases. The emitter voltage decreases due to decrease in the resistance across the PN junction.
Due to the resistance across the PN junction.
Across the PN junction. The resistance reduction results in increase in current from the IP to IV, where IP is peak current and IV is valley.
IV is valley current.
The reduction is due to intermodulation of the current. The reduction in resistance and current increase is due to intermodulation.
So finally, we can have
The saturation region.
saturation region.
This region is beyond the valley point region. It is beyond the valley point
region, and it represents a point where
and it represents a point
where
there is no increase.
there's no
Increase in conductivity.
there's no increase in conductivity, and therefore the
Emitter current will remain constant. There's no increased conductivity, and therefore the emitter current will remain constant.
So we can have some of the applications of
UJT applications.
Number one,
You can use this in trigger circuits. Trigger circuits.
another thing we can use this
In trigger circuits, particularly switching, switching.
Another place you can use is
This is in sawtooth generators. Sawtooth.
we can also use this in what I refer to as
Non-sinusoidal oscillators.
And lastly, you can use this also in tuning circuits.
So we're going to have our third special semiconductor device is programmable UJT, sometimes referred to as P-put.
Programmable
UJT, programmable unijunction transistor.
So you shall also have a sketch of that. When you have a sketch of this
Will appear this way. Construction. This is construction. Then we're going to have the equivalent circuit of this. This is the equivalent diagram, equivalent circuit. You can also have a symbol on how the symbol looks like, so that when you see the diagram, from the symbols, you can be able to interpret this. So this is the symbol. So you can, when you look at this diagram, this is the physical construction on how it appears. And you are going to realize it has got two PN junction, but the gate is connected on only one junction. The other gate is not connected. So basically, for us to operate it, we need to apply an anode voltage or a voltage that's greater than the PN junctions. When you look at this, we're talking about two types of transistors connected. The collector is connected to the base of the other. If you have this collector and this is the base and this is the emitter, we're going to like this is the collector, this is the base, and this is the emitter. The base, the collector of one of the transistors connected to the base of the other, and because of that, we are able to keep the conduction in cyclone, whatever as a continuous mode. So when we want to operate on something, or we want to do something to turn it off, then we must be able to stop one of the transistors first, or reverse the voltage so that it turns off before the other one is able to turn off. So we are able to explain this, what is. So the difference between a programmable UJT and a normal UJT is that this can only take a code or a program that enables it to function like is a very unique way. But what happens is that the code is able to put this into a situation whereby the switching is controlled when a code is able to be initiated. So a programmable UJT, a programmable UJT operates in the same manner, like an ordinary UJT, except that it is programmable. It is programmable through the gate terminal.
Through the gate terminal.
So we're going to talk about the fourth special semiconductor. We talk of what?
Silicon control switch.
SCS. Silicon control switch. Silicon controlled switch, SCS. So we also need to sketch a diagram for this so that we understand it the simplest way possible. So when you look at this diagram, these two transistors that are connected on back to back, and in this case, for us to talk about the switch or the SCS, then we have whatever I refer to as, it has got two gates, gate A and gate B at this point here. So for us to explain its operation, we must assume the initial state. We must assume that the initial state, so that we are able to have the conductivity. So this, when I merge these two principles this year, then we're able to talk as, when we're able to explain how this is able to work. So we must assume the initial state. So assuming that the transistor Q1 and Q2 is off, and we want to start the initial process. So when we assume the Q1 and Q2 is off, and we apply a voltage at gate A, that voltage at gate A will bias the transistor Q1 into saturation or into conductivity. When that one is biased Q1 into saturation conductivity, then the current through the anode is going to flow and will be amplified through the transistor, and the collector current is able to flow through here. It goes to flow through to GB, and we'll be able to turn on the transistor Q2 because we'll have an amplified current flowing through this point and able to turn on this. So the conductivity is such that we're able to have the conductivity of this, and this is going to turn on. When this one also turns on, it's going to amplify its current through this path, and we shall have a current that's going to flow through back to the transistor Q1. So we realize that as long as one of the transistor is on, the other one will turn on. So for us to turn off the device, then you must disconnect or the supply. You must turn off one of the transistors so that it turns off, it goes into the cutoff, so that there's no amplification, and with the time, there's no amplification, and with time, the other transistor is going to turn off. Alternatively, when it goes to the turn off, then there's a disconnect to the base of the secondary transistor. So if this one is off, that means that this one is not going to conduct. And because of that case, then this transistor will turn off automatically, and that's how we turn off the SCS. So the initial condition is that we must assume the transistor, all the transistors are off. And then we explain this in details as follows. Assuming QA and QB, Q1 not QA, it's Q1 and Q2 are off, and a voltage is applied, and a voltage is applied, at gate at gate A, which is connected to the base of the transistor Q1. If a voltage applied at gate A connecting Q1 is enough, or greater, the transistor Q1 is saturated, what I will also refer to as turned on. And hence it conducts, and hence it amplifies, inputs from the anode terminal. So once the transistor QA turns on, it amplifies the input from anode terminal. That amplified input is going to connect to the base of the transistor Q2. The collector current IC1 is going to flow to the base of transistor Q2 and turn it on. Hence, there will be further amplification. Amplification of current that flows back to the base of transistor Q1. This results in a continuous conduction. And amplification of initial conduction, amplification of current flowing.
through the switch.
On.
Stand
Off. Stand off. Stand off
by
this is stand off by turning off the gate current, by turning off
the base current of
in transistor, turning off the base current of either the transistors Q1 or Q2, whether it's a Q1 or
Q2. Turning off the current, the transistor Q1 or Q2. Then we talk of the application.
where can we
Find this,
and from the operation
itself we talk about
counters, registers, or counting devices. Counters, registers, and timing circuits. When we're using this as counters, is that we shall be able to register an increment in the amplitude, and that one will not talk of the counters. When we're talking about the timing circuits, you can be able to know when the system is going to be turning on, or when a certain level is reached, that's going to be talking of the timing circuits. Then we talk of number two is the pulse.
Generators.
Pulse generators.
We're talking about
Pulse generators is because you are able to produce an output across the on the collector terminal of one of the transistors. So it's going to tell the pulse.
And then talking about
the voltage sensors. Number three is voltage sensors. And lastly,
number four, on the
type of oscillation and the type of application you can have that as oscillators. Then we're going to have another device,
silicon control rectifier.